Hello and welcome to another video in this series looking at how to achieve structural steel design using AI and retrieval augmented generation. In this video, we turn our attention to the design of cold-formed steel structural members, according to AISI S100. As discussed in previous videos, the effective width method of design in AISI S100 has attracted criticism due to its complexity. The calculations for gross and effective section properties are onerous, particularly when flexural iterations are required, and likewise the calculations for distortional buckling. The solution is to make a smart AI do all the boring calculations for you. In this video, Claude AI is tasked with a common, and particularly computationally demanding, design case of an I-section beam column consisting of back-to-back channel sections with edge-stiffened flanges. Such I-section beam columns are common in cold-formed steel portal frames and load-bearing external walls. In order to gather all the sections from the different chapters of AISI S100, Claude calls the connected RAG database of the specification 14 times and collects details from 19 different sections. Claude then breaks the problem down into component parts and uses the results from RAG to write 7 different Python codes, each calculating different aspects of the design: axial, flexure, shear, interactions, distortional, fastener spacing, etc. The results are detailed in the report generated by Claude, which we'll go through on the left. On the right, we have Claude doing its thing, working away diligently on the design. It's sped up so you can see the full 29-minute one-shot design without any human intervention. This is example 6.2 from the seminal cold-formed steel design text by Yu, Labaub and Chen, 5th edition. Claude gets a design load P of 0.73 kips, while the solution in the textbook is 1.1 kips. The report begins with an executive summary and problem statement, then the material and geometric properties are established. The structural analysis of the two-span continuous indeterminate beam is then undertaken to determine the bending moment diagram. The effective lengths are then established based on the beam bracing. Next, the axial compressive strength is calculated, considering yielding, local, global, and distortional buckling limit states. First global buckling, then local buckling using the effective width method, and then distortional buckling. The nominal axial strength is then established. Next, the flexural strength is calculated, considering lateral torsional buckling, local buckling, and distortional bucking. Following this, the shear strength is calculated. Finally, interactions are checked, including axial compression and bending and shear. Some check are then undertaken for built-up sections generally, and for back-to-back channels in flexure. The report is finalized with conclusions, notes, recommendations, and references. Set up your free structural steel design RAG to use with any AI LLM model. Step 1. Download the free RAG vector databases from steelcoldform.com. Step 2. Follow the instructions on the engineering RAG page to set up the API for running queries. Step 3. Connect your LLM of choice to your RAG API, allowing your AI agent to query your RAG as required. RAGDBs were created from free PDFs of the specification provided by AISI, AIC, and ANSI. All RAGDBs are provided free to promote the use of steel.